So in this video, we're going to look at the fundamental concepts of charge and current. So thinking back to wherever you were introduced to your fundamental chemistry or physical principles, hopefully you remember that charge is one of the two fundamental properties that really causes matter to behave the way that it does from a physical perspective. Namely, because matter has mass, it exhibits a phenomenon associated with attraction due to gravity. And in addition, because it has charge, it's subjected to electrodynamic forces. So at the atomic scale, thinking back to whatever model you may be comfortable or familiar with, maybe something as simple as a Bohr model, hopefully you remember that charge is polarized. There is positive and negative charge. And at the most fundamental level, it is discretized into this idea of a proton and electron. And each of those have different properties with respect to their location within the atom, along with their mass and so on. If you think about most models have protons kind of clustered in the middle and this dense structure known as the nucleus, and then electrons kind of orbiting around the outside of that in motion. And the reason by Newton's law of inertia that they just don't keep going at whatever trajectory they're moving on is that fundamental attraction to the protons in the nucleus. So hopefully you remember fundamentally that these two polarities of charge, that if they're alike and in proximity to one another, they want to move away. And if they're opposite, they're attracted. So in the actual circuit analysis examples that we're doing, we're predominantly going to be dealing with negative charge carriers. And that's not to say that there aren't any underlying phenomenon in electrical and computer engineering where the charge carriers are positive. In fact, they're quite common. Things like lithium-ion batteries, p-type semiconductors, and so on. However, when they're interconnected in a circuit, we're going to be, as we'll see later on in this lecture, kind of concerned with just modeling all of these as these simple electrical two-component elements, where we're really interested in how charge flows in and out, not necessarily what's going on the inside in the form of abstraction. And all of those charge interconnections are traditionally going to be some sort of metal. And if you think about the way that metal works, the mobile charge carriers in that case are electrons. So what we're going to see is we have a little bit of a contradiction because the fundamental SI unit of charge is defined in terms of a positive quantity, but what really is going on under the hood, at least in the circuits at the input and output interface, is electrons are moving. And we'll handle that when we get to that point. But in addition, the two key things you want to take from this is that charge is conserved as it moves around the circuit. That will be the basis for one of our fundamental laws that we'll look at soon, Kirchhoff's current law, and that charge in motion. When charge is moving, we refer to that as a current. So in engineering applications, as I mentioned, the majority of the time we're going to be working with charge that's on a much larger scale than those discrete units that we see within the atom. And that is reflected in the choice of the SI unit of charge, which is 1 coulomb. A coulomb is nothing more than a very large bundle of a bunch of those fundamental units of charge. Particularly, it's defined as being a big bundle of positive charge or protons. So that kind of leads to that idea of conventional current versus electron flow that we'll see kind of revisit later on in the actual circuit analysis portion of the course. But here is a conversion factor. This is the one your book presents. It's not traditionally the one I see. Usually I see it the other way. But 1 proton, which is a very small discretized unit of charge, is equal to 1.602 times 10 to the negative 19th. So think about how many times you would be moving the decimal to the left there. Coulomb. So you can use this as a conversion factor to convert between expressions of charge, either in coulombs or fundamental units of protons or electrons. Just if you're converting to electrons, be careful to add that additional negative sign. So how do we formally define current? So current is nothing more than the flow of charge, or as your text puts it, charge in motion. The SI unit of current is the ampere. By definition, if you have 1 ampere of current, that corresponds to 1 coulomb of charge passing a fixed cross-section in a circuit per second. And you can kind of see that visualization here. If I have some carrier of charge and I can cover the entire cross-section, and I can count how much charge kind of penetrates that cross-section within a second, keeping in mind, as we'll see in a minute, that you have positive and negative charge and you can have multiple directions. So there's a lot going on here. But in short, if there is 1 coulomb of charge passing in a second, that is said to be 1 ampere of current. So when you think about current, it really kind of drives all of the fundamental phenomenon that we kind of come to not even think about. It's ubiquitous in our daily life with respect to how do we actually get power from wherever power is being generated. So the actual passing of current through transmission lines is how you can deliver power over a distance. That's one way that kind of current is fundamental in our modern electrical systems. In addition, if you have a current that is varying with time, and as we'll see a little bit later, what that would mean in practice is that the direction of flow is always changing. You can actually encode information in the way that current changes its direction over time. And if you place that current on a physical device, such that the physical dimensions result in wavelengths that are adequately, the size of the object is large relative to the wavelength, or if it's electrically large, that device will radiate. It has the capability to take and transmit or receive electromagnetic waves. So you can take currents and actually turn them into waves. And since that information is actually encoded in how the current is changing over time, that is what really forms the basis of how we communicate information over a distance. So things like 5G and whatnot are all driven by the ability to code time-varying information into currents. Current is naturally kind of a vector quantity, if you think about it. We have an amount, or how much charge is actually moving, and we also have a convention to describe the direction. Now, one of the things that makes this incredibly complicated is we not only can have negatives resulting from having on a diagram the incorrect direction, but a negative could also represent the flow of negative charge versus positive charge. So by definition, remember that an ampere of current is a coulomb per second. So what this means right here is you have 3 coulombs per second moving to the right. An equivalent way to say that is that there are negative 3 coulombs per second moving to the left. So much like when you deal with vectors, you can kind of swap the effect of this negative sign with changing the direction of the arrow. So that's something that we'll get to see a lot more in later detail. So let's look a little bit at the fundamental kind of calculus-based definition of current and its relationship to the cumulative charge function. So this function Q of t is the cumulative charge function. It just basically counts how much charge has passed a reference point in the circuit relative to some reference time. That can be t equals 0. And if you have this expressed as a function which is differentiable, you can express the current as a function of time by simply taking the first derivative with respect to time. So I is dq dt. Note here, I don't have to show the dependence with respect to t. It's just assumed to the right. And in addition, in circuit analysis, traditionally, lowercase letters are reserved for time-varying quantities. So when you think of this, again, just note that if you have a positive current, it actually corresponds to the flow of positive charge by what is known as conventional current theory. So if I were given this function Q of t, if I don't have an expression for it, and I just have to kind of eyeball what the corresponding current would be by envisioning the instantaneous rate of change or slope of the tangent line, I can draw little tangents here, and I can see up until about, what does that look like? 1.8 seconds, the current will be negative, at which point the slope of the tangent line here at the local minimum is near 0, and it will turn positive. So it's going to be, the current would be some kind of function like that. In addition, if you are given an expression for current and you basically want to count how much cumulative charge has passed a reference point in a circuit, you can do that via integration, right? If you just separate this differential equation here, multiply both sides by dt, what you would get is dq, or small changes in charge, occur when you have a current that exists over some infinitesimal chunk of time. So dq equals I dt. And then if you integrate that over whatever time of interest and adjust for your initial condition, you can get an expression for the total cumulative charge at some point in time. So one thing that you want to be aware of is how currents actually exist as functions of time in practice. They can be constant, as you see here. This is what is referred to as a direct current, or a DC current. They can kind of oscillate or be sinusoidal over time. Since the polarity or the sign of the charge is changing from positive to negative, we will call this an alternating current or an AC current. In addition here, you can have a current that is exponentially decaying over time. These occur as first order responses in like RC and RL circuits, as we'll see a little bit later on in the course. And you can have kind of a mixture of the two sinusoidally damped responses in second order systems when you have two reactive components, and all that is coming. So let's look at a couple example problems here. One, the total charge stored on an 8 millimeter plate is minus 10 to the 12 coulombs. How many electrons are on the plate? So if you go and you navigate to the actual solutions here, I had to re-record this whole video because I was just quickly writing these solutions and had an error in them and had to re-upload. So that's why I had to refresh my browser there. But hopefully this will come up soon. But let's talk about how we would do it while we wait for it to actually come up. Basically, all we're doing is a little bit of a unit conversion here, right? We have a quantity of charge measured in coulombs. We want to convert it to electrons. So we're going to need our actual conversion factor here. And that conversion factor is this 1 proton or electron being equal to 1.602 times 10 to the negative 19th coulomb. Since we're dealing with electrons, we're going to have to add a negative sign out in front here. As you can see, I've done in my conversion. So minus 10 to the 12 coulombs. 1 electron is minus 1.602 times 10 to the negative 19th coulombs. The minuses cancel, the coulombs cancel, and we're left with this 10 to the negative 19th comes in the numerator becomes 10 to the positive 19th. When you combine 10 to the 12th and 10 to the positive 19th, you get 10 to the 31. You do that math there, and you're going to get 6.242 with 4 digits of precision consistent with the conversion factor times 10 to the 30 electrons. So not surprising, if you have 10 to the 12 coulombs, the amount of electrons, since it's a much smaller unit, will be much larger. For the second example problem, we're actually given an expression for a time-varying cumulative charge function. Q of t equals 4 minus 8t coulombs. From the moment it's switched on, we're asked to find the current flowing in the device at 3 seconds. Remember, if we have an expression for the cumulative charge function, Q of t, the current I of t is nothing more than the first derivative with respect to time. This is just a linear function, so its derivative will be constant. So this, the derivative of this function will be minus 8 coulombs per second, which is minus 8 amps. That is a constant DC current. If you were to actually graph it, and remember, it's only defined from t equals 0, so sorry about that. It's going to sit out here at minus 8 coulombs, and if we were to graph the original linear function, cumulative charge function, 4 minus 8t, it is starting up here at 4. It's got a slope of minus 8, so not surprisingly, that as this current negative 8 amperes accumulates over time, it's going to decrease the charge from the positive initial value to negative. So this writing here just says that the current at 3 seconds is the same as the current at any point in time, as long as that time is within the interval of 0 to infinity. So that is a DC current by definition. So I hope that this video was helpful, and I'll see you in the next video.